Okay, a lot to do today, so let's get started. We're going to do counting, and counting is notoriously hard. So I want to start out with a couple of problems that illustrate just that point exactly, that it's difficult. So the first is a fence is 100 feet long with a post every 10 feet, and how many posts are there? And it's very easy to imagine a person saying to themselves, okay, 100 feet, 10 per, I'm looking at 10 posts, and the answer is wrong. Imagine that instead the fence was 10 feet long, and it has a post every 10 feet. How many posts? Well, of course, clearly there's two. So that's to say you've got an off by one error, and off by one errors are very, very easy. I make at least one a week. So you got to make yourself say, is this an off by one error? And even then, you still make one a week. So you got to make yourself say, is this an off by one error? Counting is an area where traditionally people make a lot of mistakes because it's very easy to make mistakes. Another example, compiler loads 50 memory locations starting at location 325. What's the next free location? And again, very easy to make a mistake. I'm not saying what the answer is for the moment. I'm only saying that reading that, you have to say to yourself, this is just like the fence post problem. I got to make myself think of what is the right answer. I got to make myself think so I don't make an off by one error. So in this case, you might say to yourself, okay, suppose instead of 50 locations, suppose it was going to load one memory location starting at location 325. Well, so it puts the data into 325, and the next free location is 326. So the answer clearly is going to this problem is going to be, if there are 50 memory locations, is to take 325 plus 50. 375 will be the next free location. And again, that could strike a person as one too few, but you got to force yourself to think what's the right answer, and even then you still get it wrong a lot of times. Another example, frog on a stream wants to get to the top of a 10-foot high bank. The bank's slippery, so with every hop of 2 feet up, he slides 1 foot back. How long does it take him to reach the top of the bank? So now you're a little cautious. You're like, I think it's 2 feet up, 1 foot back. I think he makes 1 foot of progress every time. What's wrong with that? So you say 10, and the answer is not 10, because when he's at the 8-foot mark and he jumps up 2 feet, now he's out, so he doesn't slide back. So again, that's sort of off by one error, and you have to be wary. You have to say to yourself, okay, I've made this mistake many, many times before. Let's not make it again. Counting, that's a general theme to accounting, is it's very easy to make mistakes. Even very practiced people consistently get them wrong. You have to, as much as you can, you have to seek to be disciplined about it. How many 3-digit integers are divisible by 3? So this is really the point of this example, is that it depends on what you count as a 3-digit integer. Do you count 100 as a 3-digit integer? Surely everybody would. Do you count 999 as a 3-digit integer? Sure, everybody would. Do you count 087 as a 3-digit integer? What about 000? What about negative 123? So that is to say, one of the problems that a person is going to see in these counting problems is that you have to force yourself to be careful about thinking through the question, thinking through what it is that you're counting. Okay, so just as a for instance, I personally would say that the intent of the question probably, well, I wrote the question, so I know the intent of the question, but the intent of the question probably was genuinely 3-digit integers, so that 087 wouldn't count, and neither would negative 087, neither would negative 123. So the first 3-digit integer that's divisible by 3 is 102. Because 100 isn't and 101 isn't, so 102. And then the second 3-digit integer, the final 3-digit integer that's divisible by 3 would be 999. So I would take 999, subtract 102, and ask myself, okay, so I'm going to divide that by 3, 999 minus 102 divided by 3. So let's try that. 999 minus 102 divided by 3, if I can make the thing come up here. There we go. No, wrong one. There we go. 999 minus 102. 999 minus 102 equals, divided by 3, 299. And then I would say to myself now, is that off by 1? Should it be 300? Should it be 299? Or should it be 298? Well, I'd say to myself, 102. If I counted all the three-digit integers from 102 to 102, it would be 102 minus 102 divided by 3 and add 1. So I'm thinking I got to add 1 to this. I'm thinking that the total answer is 300. Okay, so again, a caution there about defining terms and about being wary of making the kind of mistakes that a person has made many, many times, hundreds of times. Okay, so now we get into sort of the meat. Having been cautioned, we get into the meat of counting. Okay, so the first and major counting pattern is possibility trees. So you're going to ask a middle school math class. You say to them, I know a person who has 2 children. And I happen to know because I've been in the gym with this person and they've referred to one of their children. So I know that one of their children is a girl. What's the chance the other one's a girl? So most people will reason something like this. Well, they'll say, well, I have no information, so it must be 50-50. But that's not right. Because if you list all the possibilities and count, these are the 4 possible families. You could have 2 boys, you could have had a boy and then a girl, you could have had a girl and then a boy, and you could have, no boys and 2 girls. So when you count, if you know that one is a girl, at least, what's the possibility the other one's a boy? Then you see that the possibility the other one's a boy is 2 out of 3. So the possibility they're both girls is 1 out of 3. So again, there's this sense of wariness. There's this sense of laying it out carefully and making sure to enumerate all the possibilities. And these trees are our main tool for enumerating all the possibilities. Here's another one. Matches in women's tennis end when one person wins 2 games. How many ways could a match go? So a person thinks to themselves, well, I could have player A wins or player B wins. And then for the second game, A or B, it's sort of stuff. And so you end up with, again, a tree of possibilities, and here we go. Player A wins, player B wins. Player A wins again, that's it. They don't play a third game because the first player has won 2 already. So we're looking at here counting all the ways in some careful manner. It's not a question of saying, well, you can have 2 winners in each game, and so 3 games, and you're looking at the 2 to the third is a total of 8. That's not right. You have to count them carefully. Turns out to be 1, 2, 3, 4, 5, 6 ways. This is called a possibility tree. The line segments, like that one and that one, are edges, and these here are called nodes. At the top, that's called a root node. Interior nodes are the nodes that have children. For example, this is an interior node because it has a child. This is an interior node because it has a child. This is an interior node because it has a child. A node that does not have a child, like this one or this one, and this one is called a terminal node. The level or rank of a node is the number of edges between it and the root. Let me look at this node right here. What's its level? What's its rank? 1, 2, 3. So it's at rank 3. The root node, what's its level or rank? Don't be fooled. How many edges are between it and the root? 0. So you start off by counting as rank 0, then rank 1, then rank 2, then rank 3. And the height of the tree is the maximum level. So this is a height 3 tree. I know it grows down, but that's just a typographic convenience because it's easy to add stuff at the bottom, that's all. Okay, how many games are there of scissors, paper, stone? I hope everybody knows how to play scissors, paper, stone. And I just made up a tree and counted them. That's no more complicated than that. So the first player can play scissors or paper or stone, and the second player can play paper or stone. If both players play scissors, then it's a non-game. It's a do-over. Paper wins, of course, of these 2. If the first player plays paper, then it's scissors or stone. Again, if you have 2 papers, that's a do-over. Stone wins here. And if the first player plays stones, so there's a total here of 1, 2, 3, 4, 5, 6 possible games. A computer system limits passwords to 8 or fewer characters, and the first character has to be a letter, and how many passwords are possible. So you ask yourself, the first character has to be a letter, and then the remaining characters have to be either either letters or numbers. Okay, I'm going to count those as characters. How many passwords are possible? So the simplest thing to do here is to say to yourself something like, well, I can have 0 length passwords. I can have length 1 passwords. I can have length 2 passwords. Oh, I got to get rid of that darn thing. There we go. I got rid of the wrong thing. There we go. I can have 0 length passwords. Now the statement of the problem says the first character has to be a letter. So I'm going to say no. But if you want to count 0 length passwords, because 0 length passwords are allowed, okay, so you're going to add that in. 1 length passwords? Well, it's got to be a letter, so there's 26 of them. Length 2 passwords? Well, the first character has to be a letter, so you're looking at 26. And then each of the 26, I'm going to say letter or digit. Of course, it depends on what you count as a character. But I think if I say letter or digit, there's 36, 36, 36, etc. So the total number of terminal nodes is 26 times 36, I think. And I think a person can see up to length 8. Where you have these tremendous trees with all kinds of, and I think you end up with 26 times 36, that's length 2, times 36, that's length 3, times 36, that's length 4, times 36, that's length 5, 36, that's length 6, 36, that's length 7, 36, that's length 8. So 1, 2, 3, 4, 5, 6, 7, 26 times 36 to the 7th power. That's a lot. That's a lot. Let me count that. So I'm going to use Sage here, the calculation software. And I'm going to ask it, what is 26 times 36 to the 7th power? And that's a lot. That's a lot of passwords. I don't know how many. So let's see. 1, 2, 3, 4. I don't know. It's a lot. It's a lot. That's all I know. Okay, let me pop that down. Oh, I popped down the wrong thing. Pop down the wrong thing. Pop up the right thing. There we go. Okay, so the basic answer is a lot. If you tried to guess them one at a time, you'd be out of luck, completely out of luck. How many games are there of tic-tac-toe? Now, tic-tac-toe is an entirely different matter because you can draw the tic-tac-toe tree. You can say, well, the starting player can put the X in box 1 or box 2 or box 3 or box 4 or box 5, box 6, box 7, box 6. So there's 9 possible branches at the first level. And then at the next level is 8 possible branches. But then you start running into this women's tennis game thing where sometimes the game is over early before you fill in all the boxes. And so you have to not count those as further. So what's the sensible thing to do? Well, of course, you can get a big piece of like butcher paper and lay it out, and then it'd probably take you, say, I don't know, an hour. Or you could get a computer to do it. And that would take you, well, if you were doing it in Java, it'd take you a week or so. But if you did it in a sensible language, it might take a couple hours. So you could count the number of games of tic-tac-toe, in some sense, in the brute force way, by simply having the computer count them all. What about chess? That's just not possible to count the number of games of chess on butcher paper or with a computer at this stage of history. It's just simply not possible. You can make an estimate, but we just simply don't know. Okay, but so one thing we're seeing in all this talk is that there are some patterns to counting that you can rely on, and in particular, you can rely on regularities in the tree, just like I had 26 times 36 times 36, etc. Some trees have a pattern to their branching. Here's an example. Old-fashioned Vermont license plates had 2 digits, then 2 letters, then 2 more digits. So how many strings are there of that form? 2 digits, 2 letters, 2 more digits. So how many strings are there of that form? So let's see. So 2 digits, 1, 2, 3, 4, 5, 6, so that's 10. Each one of those has 10. Each one of those has 26. Then 26. And then finally it ends with 2 digits, 10 and 10. So we fill this all out, you get this tremendously big tree, but it's 26 times, it's 10 times 10 times 26 times 26, etc. Let's see what, come on. There we go. Let's see what Sage makes of that. So 20, so that's 10 to the 4th times 26 squared. So a lot. Not a tremendous amount, but about 6,760,000. So a lot. I'm pretty sure there aren't 6 million cars in Vermont. They no longer make license plates that way, so they must have had another reason to abandon that scheme for license plates. Till recently, phone numbers in North America had the form NYX, NNN, XXX, where N is a digit between 2 and 9, Y is a 0 or a 1, and X is between 0 and 9. And now phone numbers have the form NXX, NXX, XXXX, how many new numbers were created in the expansion. So the question basically asks you to calculate how many phone numbers are there of this form, and how many phone numbers are there of the new form, and do the subtraction. Okay, so let's calculate how many phone numbers of the old form and like that. So time for a new piece of paper. So we're looking for NYX. There we go. I'm looking for NYX. And then I forgot already. And then NX, and then XX, XX. NNX, and then XXXX. Okay, so how many phone numbers have 2 through 9? So 2 through 9 is 2, 3, 4, 5, 6, 7, 8, 9. That's 8. So we're looking at 8. 0, 1. 2. 10, 8, 8, 10, 10, 10, 10, 10. Okay, and the new form is NXX, 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 XXXX. So I think I'm looking at 8 times 10 times 10, 8 times 10 times 10, and 10 to the 4th. So you take the larger one, subtract the smaller one, that's your answer. How many numbers less than a billion contain the digit 1? How many numbers less than a billion contain the digit 1? Well, the problem with numbers less than a billion that contain the digit 1 is that if you do something like how many numbers less than a billion contain the digit 1 in their last place, what's a billion? That's a million, right? So this is a billion. Okay, so 1 billion. That's a big number. How many numbers less than a billion contain a 1 in their last place, in the least significant place? I could figure that out. It's 1/10 of the total. How many contain a 1 in the next to least significant place? I could figure that out. It's also 1/10 of the total. And now I'm asking myself something like, but what if it says a 1, 1? I've double counted. Oh, that's annoying. I've double counted. That's no good. That's no good. That's no good. So I'll have to subtract out the double counts. And then when I add a new one, then I'm worrying about subtracting out the double count and adding in the triple count. And here's an easier way. Let's figure out how many don't have a 1. Got some piece of junk there. Piece of junk on the desk. How many don't have a 1? Okay, well, if you're going to be less than a billion and not have a 1, then your choice for final digit, there are 9 choices. And for this digit, there are 9 choices. And for this digit, there are 9 choices. And for this digit, 9, 9, 9, 9, 9, 9. I think I got that right. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 to the 9th. 9 to the 9th, I said. Okay, so how many do contain a 1 is a billion minus 9 to the 9th. Okay, so one lesson about counting that we see in all these things, but one lesson about counting is that sometimes there's a complicated way, but there's also an easy way. So sometimes a certain amount of ingenuity, sometimes a tremendous amount of ingenuity, sometimes a certain amount of ingenuity is called for. Permutations. If a tree with h many levels is regular in that at each level every node has the same number of children, then the total number of terminal nodes is the product of the number at each node, C1, C2, etc. Number at each level, C1, C2, C3, etc. Okay, and the proof is by induction on the height, and I'm going to go through it because it's very straightforward, but it's a straightforward proof by induction. If the tree has height 1, then it has a single root with C1 many children, and there are obviously C1 many terminal nodes because the tree has height 1, then every one is a terminal node. Okay, now we go to the case of the inductive step. So now you assume the height is bigger than 1, and the statement is true for all trees of height less than h. So you consider a regular tree of height h, and also consider the subtree t hat that you obtain by omitting all of t's terminal nodes. So you've fallen back to the prior level. Suppose that the statement is true for t hat, so it has this many terminal nodes. But each of those terminal nodes in t hat has c sub h many children by the statement of the theorem, and so in total the tree T has C1 through C2 times all the way up to times CH many terminal nodes. So it's a straightforward induction. A lot of these things are proved by induction. 9 horses are in a race. How many win, place, show, finish orders are possible? So we find ourselves 9 horses in a race. We're worried about win, place, show. We find ourselves, got to the wrong place. There we go. We find ourselves doing the thing that we, having a sort of official justification for exactly the pattern we've been working on so far. So 9 horses in the race. How many could win? How many could place? And now is the only tricky part. Person says to themselves, why all 9 could be second place horses? No, that's not quite right. If you think of the tree, the root node is going to have 9 children, possible winners. But if you pick any node on that tree, and you've already decided who's the winner, it doesn't have 9 children, it has 8 children, because the winner can't be the second place horse also. Okay, so we're not looking at 9 times 9, we're looking at 9 times 8. And now, of course, the person knows the pattern 9 times 8 times 7, and you ask yourself, what is 9 times 8 times 7? And 9 times 8 times 7, and it's 504. It's kind of a lot, actually. So if you go to the track and they ask you to to pick isn't that the trifecta where you bet on win, place, show? Then there's just if you're just wildly guessing, it's very hard to get it right. 8 people take a test. How many rankings are possible? So again, the main thing here is that the answer is not 8 times 8 times 8. That's not the answer. It's true that the second place person could be anybody, but if you look at the tree, when you say to yourself, the root node has how many children? The root node has 8 children. For every one of those children, there are only 7 children. Okay, so now we're getting 8 times 7 times 6 times 5 times 4, etc. And so let's do that multiplication here. I told myself I was going to multiply these at least up till some point. So 8 times 7 times 6 times 5 times, so 8 times, come on, 7 times 6 times 5 times 4 times 3 times 2 times 1, and I end up with 40,320. Which again is surprisingly large. Combination lock uses 3 numbers out of 36. How many combinations are possible? And again, you can't use the same number twice. So 3 numbers out of 36, so we're looking at 36 times 35 times 34. 36 times 35 times 34. I understand that actual combination lock doesn't work quite that way, but we'll go with that. So 36 times 35 times 34 comes out to be 42,840. So nearly as many, or nearly the same number as the horses, as the rankings in the class with eight people. So again, pretty big numbers, surprisingly big numbers. So the definition is a permutation of a finite set is an ordering of all its elements. Somebody wins, somebody comes in second place, like that. An R permutation is an ordering of a size R subset. So when I was looking at the permutation lock, I was only interested in 3 numbers at a time, not all 36. So the example there is I take the set. Do you see the curly brackets around the set? Curly brackets, this is a set. Spades, hearts, clubs, diamonds, and I order it and I make a permutation, which I call F. Clubs, spades, diamonds, hearts. Now that's diamond brackets, so those are ordered. That's a sequence, not a set. A 2 permutation is you pick 2 of the 4 things and you order them. A set with n elements, the number of permutations is you take just like I took 8 times 7 times 6 times 5, etc. You take the numbers from n on down and multiply them together. If you're looking at an R permutation, just like with combination locks, I said 36 times 35 times 34, I stopped after I got to 3 numbers. So too here, you multiply the numbers from n on down, but you stop after R many numbers. If you take the numbers from n on down and stop after R many numbers, you might think, you'd be wrong, but you might think that it would go n down through n minus R, but it's an off by 1 error. If you actually do it out on your fingers, it's n out to n minus R plus 1. So the factorial of n, I know everybody knows this one. The factorial of n is n factorial is the numbers from n on down multiplied together. The rth falling power, n raised to the r with an underline under it, is the numbers from n on down, but only multiplied together r many of them. So down to n minus r plus 1. And the falling power is something that we're going to see a lot of. It has lots of notations in the literature. This one here, n to the rth falling power notation, that was invented by Knuth, and it's becoming more and more common. This is sort of more old-fashioned notation. This one in particular was very common when people had typewriters and subscripts and superscripts were trouble. This is the one that happens to be printed on my calculator, so you may have it on your calculator. It's kind of a compact notation. You see that? Another thing that you may have learned in high school, you may have learned this in high school, as you take n factorial on top and n minus factorial on the bottom of a fraction. Of course, when you do all the canceling, everybody cancels except for the terms that we're interested in. So you might have seen n to the rth falling power. You might have seen it written this way. Again, it's becoming increasingly common to do this, but you may have seen it in the past. It's nice to connect. You may have seen it in the past written this way. One of the things I've been trying to talk about, I've been trying to go through here and calculate some of the numbers, is what's called combinatorial explosion. These numbers get big. These numbers get big very fast. So just as an example, here are the first few factorials. The numbers from 4 on down multiplied together make 24. The numbers from 5 on down multiplied together make 120. That's only 5 numbers, and you're already up to 120. The numbers from 10 on down multiply together to make about 3.5 million. Knuth, for example, cites 10 factorial as in some sense the most steps in a practical computation. Let's imagine that you're taking, say, the 26 letters in the alphabet, and you're going to scramble them all up, and so you're asking yourself how many possible scrambles are there. So you're looking for the factorial of 26. That's a lot. Let's suppose that you took the 52 cards in a deck and you scrambled them up. That's a real lot. These numbers grow tremendously quickly. That number is just staggeringly large. So if I scramble up a deck and you scramble up a deck, it is basically impossible for us to get the same scramble. Even if I scramble the 26 letters and you scramble the 26 letters, it's basically impossible for us to get the same scramble. That just basically can't happen. Did I not pop it? There it is. Sorry. Okay, so if you scramble up the 26 letters, look at that. That's a big number. If you scramble up the 52 cards in a deck, look at that. Oh my God, that's unbelievable. The next question on the slide is, it says you have a message encoded by a substitution cipher. So for A, you're putting in some letter. For B, you're putting in some letter. You're scrambling up the letters here. Computer will try all the possible scrambles and scroll them by on the screen, and maybe it'll scroll them by at 10 per second, and you're going to watch and pay attention, and when you see one that looks like a sensible sentence, then you'll hit the stop button. Okay, how long will that take? So let's take 26 factorial. 26 factorial, that's how many ways there are to scramble the 26 letters. Okay, and let's divide that by 10 per second. So that's the number of seconds. Didn't make much of a dent, did it? And let's do that for 24 hours. At 60 seconds per minute and 60 minutes per hour. So that's how many days. Still not much of a dent. What are there? 365 days in a year. 365 is actually 365 and a quarter days in a year. That's 10 to the 18th many years. That you have not made a dent. In fact, they're about 10 to the 14th years since the Big Bang. So you're not making progress. It's not happening that way. It's just not happening. So one of the lessons of these numbers is that they get big very quickly. Think of a deck of cards, 52 cards. It is not very physically large. Scramble them up, you get an impossibly large number of permutations. Okay, well, our permutation, I want to talk about combinations next, and our permutation of a set is an ordering of a size R subset. Sometimes we don't care about the ordering of the size R subset. We only want to count the number of size R subsets. We don't care about the different orderings. And here's an example. I took the set that consists of 5 things, 5 letters, just because it was convenient. And obviously there are 5 times 4, many, 2 permutations. So it's n times n minus 1 times n minus 2 all the way down to n minus r plus 1. So it's 5 minus 2 plus 1 sort of stuff. So we're looking here at the 20. There they are. It's easy to check that it's the right number. And I don't actually care about the ordering, A, B, or B. I don't care. So I'm going to group them together in one group and say that's the one that contains this subset. A, C, and CA, that's the one that contains this subset. B, A, D, and DA, that's the one that contains this. How many total subsets do I get? And of course, I get 20 in total divided by 2 because there's 2 in each subset, and so I get a total of 10. So ignoring the ordering and taking AB and BA to be equivalent, there are 10 size 2 subsets of S. Poker hands, because that's a number that people are familiar with poker. So there are 52 to the 5 falling, many 5 permutations. So that's how many, if somebody deals the cards out, how many different deals are there? 52 to the 5 falling. Let's pop that up. Darn it, there we go. So 52 times 51 times 50, etc. So that's 52, whoops, I did the wrong thing, I'm sorry. 52 times 51 times 50 times 49 times 48. There we go. That's 5 falling. And that's a pretty big number. Pretty big number. But I'm not interested so much in the dealt hands as I am interested in what happens when you arrange them in your hand the way you like them. That is to say, it doesn't matter in what order they came. So any of the 5 factorial orders that they came to me are equivalent as far as I'm concerned. So I'm going to take the number that I just calculated and instead divide it by 5 factorial. Do you remember that 5 factorial was 120? We saw that a few minutes ago. And we get about 2.5 million. A little more than 2.5 million, 2.6 million. So an R combination is an unordered selection of R many elements taken from a set of size n. An R combination is an unordered selection. So an R permutation is an ordered selection, and R combination is an unordered selection. Permutation is order, combination is unordered. And the number of R combinations is denoted with this symbol here. Don't put a fraction bar, that's not a fraction. You read that out loud as n choose R. Older fashioned notation is to write CNR. Again, people wrote that when all they had was typewriters. Or C with a sort of pre-subscript N and a post-subscript R, and that's, for example, my calculator has. I still see that today sometimes, but this is by far the most common. The number of R permutations is N to the R following divided by R factorial, exactly as it was with poker. With poker hands. And this is a formula that you may remember from high school. It's been my experience. Folks have often seen this formula in high school. You recognize the N to the R falling as these two parts of the fraction, and the divided by the R factorial is right there. The proof is just as simple as if you want to make an ordered arrangement, you first choose an unordered set and then order it, and so that gives you this expression, and then you just solve for the N choose R, that's all. Okay, so some quick examples. In bridge, I've never played bridge, but each of the 4 players gets 13 cards, and the order in which the cards are dealt doesn't matter. Each of the players gets 13 cards, and the order in which the cards are dealt doesn't matter. So what's the total number of bridge hands? Come on, there we go. Had a little trouble getting it to work. Okay, so it turns out that to do combinations, what you want to do in Sage is you want to say binomial, for a reason that we won't get into until the next video. So binomial, and I'm looking for, it's 52 cards in the deck, and the first player gets dealt 13 cards. So that's how many hands the first player could have. That's a lot of hands. But wait a minute, there's a second player also. So I've got to multiply that by, there's no longer 52 cards for the second player. There's now 39 cards are available for the second player. So the first 2 players taken together, that's how many hands they could have. All right, but of course there's the third and the fourth player. In the possibility tree, there is no longer 39 cards for the second player. Instead, there's 26 cards available. This is exactly like the win, place, show problem, where you said to yourself, well, 9 horses could win, 9 horses could place. No, that's not right. For each of the 9 horses that could win, there are 8 possible second players. So too here. For each of the 52 cards, for the first player, you take 13, and then you go to the second player. For each of the first player's hands, there are now 39 cards available. And now, for each of the first and second player's hands, there are 26 cards available. And I'll finish it off, although it doesn't matter, because once you've chosen the cards for the first 3 players, why, of course, the third player is determined. But anyway, I typed it in, and Sage calculates a very, very large number. Not as big as 52 factorial, but still a very, very large number of cards. This is combinatorial explosion. There's a tremendous number of possibilities, even in as simple a thing as 4 people sitting around a card table playing bridge. There's just a staggering number of possible outcomes. Vermont Powerball. Vermont Powerball game involves picking 5 numbers out of 55, and for the bonus, 1 of 42 numbers. I've never played Powerball, but that's what I read online. What's the chance of winning? And of course, I grabbed the card from an online picture. So let's see. I'm looking at 5 numbers from 55, and 1 out of 42. So I think I'm looking. I might be wrong because I've never played, but I think I'm looking at out of 55. Out of 55. Choose 5, and then go on to choose 1 out of 42. So a pretty large number, Vermont. So that's what is that? 146 million. And Vermont only has 600,000 who live here. Class has 12 women and 9 men. Statistician wants to know how many class rank orderings are possible, paying attention only to gender. And this is a classic problem where a person thinks it says class rank, so I have to do permutations. But in fact, what it actually says is how many class rank orderings are possible, paying attention only to gender. So let me look on the piece of paper here for starters. So now I'm looking at class ranks. So it's going to go something like man, man, woman, 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 man, woman, woman, man, etc. So one way to think about what's happening is that I'm writing down the class ranks. I'm writing down the class ranks, and I'm reaching into a bag that contains the total number of class ranks. I forgot, it's 12 women and 9 men. So at the end is 12 plus 9 must be 21. So I'm reaching into a bag that contains 21 numbers in it. And I'm choosing the 12 men. And then the women are whatever I didn't choose. Or I could choose the 9 women, it doesn't matter. The 12 men would be whatever I didn't choose. So that is to say, I'm looking here at 21, choose 12. That's the number of ways to write M's into those slots. And then whatever I didn't pick for the M's are going to be the F's. So 21, choose 12. Let's ask the sage, what is 21, choose 12? And it says 293,000. So again, trying to emphasize how big these numbers are, they are strikingly large numbers. Some more. Next, the statistician studies the effect of years in college. How many rankings are possible? So first year is 4, sophomore is 10, junior is 5, and senior is 2. So again, I'm gonna go to the piece of paper. Need a new piece of paper here. So first year is 10, sophomore is 5, junior is sophomore. So first year is 10, first year is 4. Sorry, is 4. Sophomore is 10, junior is 5. And senior is 2. Okay, and I'm asking how many class ranks are possible where I don't pay attention, instead of not paying attention to gender, I'm paying attention only to gender. Now I'm paying attention only to class year. Okay, well, so I'm going to basically have a bag with numbers in it. That's my idea of a bag. 14 and 5 is 19 and 2 is 21. So 1, 2, 3, all the way down to 21. I'm going to reach into that bag and pull out 4. Those 4 will be the places where I put first year slots. So I'm reaching into that bag and pulling 4. 21, choose 4. And now for each of the places where I put first years, I'm going to put sophomores. Of course, in the possibility tree, there are no longer 21 possibilities available. Now, instead, there's 17 possibilities? 17. Choose 10. And for each of the placements of first and second year students, I'm going to reach into the bag and pull 5. So there must be, let's see, 17 minus, so 17 minus 10 is 7, so there must be 7, choose 5. And then at the end, if you want, you could just stop, or you could take 2, choose 2. You won't be surprised to find that if there are 2 things in a bag and you pick 2 of them, there's only one way to do that. So that's going to be the number 1. Anyway, so let's go down here to the, let's ask Sage, what do we get for a number there? So binomial, 21.4, if I could type it right. And I'm multiplying by binomial 1710, and I am multiplying by binomial 7.5. And it would be perfectly correct to go on and multiply by binomial 2.2, but it will turn out not to make any difference, so I won't bother. And again, a very impressively large number. You say to yourself, whoa, how come in this very small size class doing something that is by no means extraordinary, how come I got so many, many, many possibilities? And that's what's called the combinatorial explosion. Okay, so more permutations and combinations. So in Morse code, each letter is symbolized by a sequence of dots and dashes. For instance, A is dot dash, while T is just dash. What's the minimal length we need for sequences to have to be able to represent all the letters? And so I'm just really trying at this point some combinatorial problems, just trying to think through what are the possibilities. So I'm going to look at a tree, and I'm going to say here you could have a dash or you could have a dot, and then you could have a dash and a dot, a dash and a dot. So far I have dash dash, that's M actually, dash dot N, dot dash A, dot dot I it happens to be. How many letters? Not 4. How many letters? 4 on the bottom row, but don't forget that T is a dash and dot is an E. So this is actually a total of 6 letters. So actually we're looking at 2 plus 4 plus how many at the next level? Surely, right? For each, we get 2. So 2 and 4 is 6, and 8 is going to be, right, 14. Yes? 14 and 16 is going to be 30, and that's enough. I've got all 26 letters with some to spare. So in fact, you only need to go to length, you only need to go here to length 4. What is the minimal length we need for sequences to have? And the answer is 4, and there's some to spare. Burlington has 38,000 people. Show that at least 2 of them have the same sequence of 3 initials. So again, trying to ask some problems where it requires a certain amount of head scratching. How do you show that at least 2 of them have the same sequence of 3 initials? Well, you find out how many sequences of 3 initials are possible, and you argue that that's less than 38,000, so there's got to be a repeat. Okay? All right, okay. So how many sequences of 3 initials are possible? So for a first initial, you can have 26. For a second initial, you can have 26. For a third initial, you can have 26. So I'm looking at 26 cubed. And what's the story with 26 cubed? I hope it's less than 38,000, or else I've got a typo in there. 26 cubed, 17,576. And so, oops, I didn't pop up the thing. Sorry, that's the second time I did that. There we go. 17,536. So that's less than 38,000. So even if you spread it out as much as possible, it would still not be enough to spread out over all 38,000. There's got to be a repeat. Too many slides here. There we go. Too many buttons to punch. Consider the permutations of 1 through 9. So think about it in your head. You took the numbers 1 through 9 and you shuffled them up, and now you lay them down 1, 2, 3, 4, 5, 6, 7, 8, 9. So first a 7, then a 5, then a 2, then a 9, sort of stuff. Okay. how many of them will both 1 and 2 precede 3 and 4? So how many of them will both 1 and 2 precede 3 and 4? There we go. How many of them will both 1 and 2 precede 3 and 4? So I'm looking at something like 5, 1, 7, 8, 2, 3, 6, 4, etc. So that 1 and 2 precede 3 and 4. Okay? Well, I would reason something like this. I would say to myself, there are 9 factorial ways to permute the numbers 1 through 9. Thinking only about 1, 2, 3, and 4, there's going to be 4 factorial ways to permute them. So 4 factorial is 24. So I would think that out of the 9 factorial total number of ways to permute, if you look at any permutation of 1, 2, 3, 4, for example, 1, 2, 3, 4, that would be, I've got 1, 2, 3, 4. That would be 1/24th of the total number of ways. So all I got to do is ask myself, in how many of these do 1 and 2 come before 3 and 4? And so I'll count them. I got fingers. I can count. Well, 1, 2, 3, 4. 2, 1, 3, 4. How about 1, 2, 4, 3, and 2, 1, 4, 3. And I think that's it. In any other permutation of these 4, I would move the 4 before the 1 or the 3 before the 2 kind of stuff. So this is 4 out of the 24 total ways. So I'm thinking the answer, 9 factorial over 4/24. No, that's not right. I'm thinking it's, 9 factorial times 4/24. Excuse me. Very easy to make a mistake. 9 factorial times 4/24. So the combinatorics can be tricky. It's one of these things where you have what seems like an elementary question, but it takes some moderately deep reasoning. 30 people are candidates for a 12-person jury. How many juries are there if the ones with different foremen are different? So they pick, the foreman is the person who gets picked first. Okay? So 30 people. So pick a foreman. Do they call it 4-person now? I'm sorry. It must be. Okay, so there's obviously 30 different ways to do that. And now pick the rest. How many people are left? Not 30. It's just like the horses in the Win Place show, 29. How many people are you picking? Not 12, 11. So 30 times 29, choose 11. Okay, so there's a kind of a knack here for, there's patterns, but there's a certain amount of kind of new problems that a person sees over and over and over again. Last one for the day, been a long day. Lotto game has 2n. Oh, I gotta move this darn thing. Sorry. There we go. And I gotta move. There we go. Okay. So a lotto game has 2n many ping pong balls. Half of them are red, half of them are white. The game arranges them in a row. What's the chance that the colors are separated? That all the whites all the whites follow all the reds, or else all the reds follow all the whites? So it seems to me you can arrange the ping pong balls in 2n factorial many ways. How many of those ways it involve whites followed by red or reds followed by whites? Well, it seems to me that you're looking at, if it's white followed by red, then you're looking at arranging the whites and then arranging the reds. Okay, so let's pop up a piece of paper. So I'm going to do two cases, white followed by red. Or red followed by white. Okay, so white followed by red, it seems to me, is you arrange all the whites and then you arrange all the reds. So that's n factorial times n factorial. Red followed by white, surely that's exactly the same thing. N factorial times n factorial. So it says, what's the chance the colors are separated? So it seems to me I'm looking at 2 times n factorial over 2n quantity factorial. And again, that's going to be a big number. Both the 2n factorial is going to be a big number. The chance of that happening is going to be very, very small indeed. Okay, all right, very good. All right, so that's enough for the day, and then leave you again with just the kind of caution that that the combinatorics are very tricky. You read the problem, it seems simple, you say to yourself, oh yes, that's obvious, and then you start thinking through the ramifications, and it gets complicated very quickly. Okay, very good.